and welcome. Today we're going to be looking at question 2 on the 2012 AP Chemistry exam. We're going to be looking through this entire free response question so you get an idea of how to approach and do these questions and are ready to ace the AP Chem exam. If you like these videos or find them informative, please be sure to like and subscribe. And with that, let's get started on our question. Number 2, a sample of pure gaseous hydrocarbon is introduced into a previously evacuated rigid 1-liter vessel. Pressure of the gas is 0.2 atmospheres at a temperature of 127 degrees Celsius. And we're going to calculate the number of moles of hydrocarbon in the vessel. Alright, let's see what we can do in here. So we have part A. We're just going to use the pervert equation, which is PV equals nRT, the ideal gas law. We want to solve for the number of moles, so N equals PV over RT, and we have what we have. We know that the pressure is given to us as 0.2 atmospheres, the volume is given to us as 1 liter, and then the gas constant is going to be the atmospheric gas constant, so we're going to divide by 0.08206, and then the temperature at 127 degrees Celsius is 400 degrees Kelvin, and divide by 400 degrees Kelvin, and we get that the number of moles of gas in the container was 0.0061 moles. 0.0061 moles. That is the number of moles in the hydrocarbon in the vessel. Alright, let's keep going to the next part. Alright, so we have that oxygen gas introduced into the same vessel contained hydrocarbon, and after the addition of the oxygen, the total pressure of the gas mixture in the vessel is 1.4 atmospheres, and we're trying to calculate the partial pressure of oxygen gas. Well, let's see. So we have 1.4 atmospheres total, which is of the oxygen gas and the hydrocarbon. We subtract off 0.2 from the hydrocarbon. We get that the oxygen gas has a partial pressure of 1.2 atmospheres. That is the partial pressure of the oxygen gas. And we can move on to the next part. Alright, part C is, so it says, the mixture of the hydrocarbon and oxygen is sparked so that a complete combustion reaction occurs, producing carbon dioxide and hydrogen gas. The partial pressures of these gases at 127 degrees Celsius are 0.6 atmospheres for the carbon dioxide and 0.8 atmospheres for the water. There is oxygen gas remaining in the container after the reaction is complete. Use the partial pressures of carbon dioxide and water to calculate the partial pressure of oxygen gas consumed in the combustion. Alright, so essentially this is a kind of combustion analysis question. Right, except that instead of using the actual number of moles or masses of something, we're just given a bunch of pressures, and we're going to try to think about what those pressures could mean. Alright, so we have our hydrocarbon here. So we have CXHY, and we're trying to figure out what X and Y are, plus some amount of oxygen gas, and that becomes carbon dioxide and water. And how does that help us? Well, we have 0.2 atmospheres of the hydrocarbon, and we have 0.6 atmospheres of the carbon dioxide. So we have 3 times as much carbon dioxide as hydrocarbon, so we're going to put a 3 here. And then for the H2O, we have 4 times as much as the hydrocarbons, so it's going to be a 4 here. Alright, so the 3 carbons, the 4 hydrogens, that's going to make this hydrocarbon C3H8, but we really don't care about that. We just want to know the number of oxygens in there, and we can figure out that we have we have from here, we have 4 oxygens. From here, we have 6. So we're going to have 10 oxygens total, which is going to be 5 moles of oxygen gas per mole of reaction. We had 0.2 moles of reaction to get rid of all the hydrocarbons. So we're going to lose, so we had 0.2 atmospheres worth of hydrocarbon. So we're going to have 1 atmosphere worth of oxygen. So we're going to have 1 atmosphere is what was consumed in the reaction. That's how much was consumed. And now we are asked to, on the basis of the answers above, write the balanced chemical equation for the combustion reaction and determine the formula of the hydrocarbon. Well, we just did this. C3H8 plus 5 oxygen becomes 3 carbon dioxide plus 4 waters, and of course we can our actual hydrocarbon itself is C3H8, and that is it for this part. Let's keep going. Alright, so we're asked to calculate the mass of the hydrocarbon that was combusted. Well, we can go all the way back to part A, and we found the number of moles of hydrocarbon in the vessel, and it was 0.0061 moles. So now what we're going to do is we're just going to take those 0.0061 moles, and we're going to multiply by the molar mass of C3H8. Well, for 1 mole, well, we bust out our calculator, we have our 3 times 12.01 for carbon, our 8 times 1.008 for hydrogen. We add them together, and we get the molar mass is 44.094 grams per mole. So multiply that by 0.0061, and that gives us total to how many significant figures? We're going to 3 significant figures. That gives us 0.269 grams of hydrocarbon, and that is our answer. Let's move on to part. Alright. Part F is, as the vessel cools to room temperature, droplets of liquid water form on the inside walls of the container. Predict whether the pH of the water in the vessel is less than 7, equal to 7, or greater than 7. Explain your prediction. Alright. So it's cooling to room temperature, droplets of liquid water form on the inside walls of the container. Now we're trying to predict the pH of the water in the vessel. Well, how are we going to go about doing that? Let's see. So what do we have in the vessel? Well, we have hydrocarbon, which is not going to be acidic or basic. We have, and then we just have oxygen gas, again, not acidic or basic. And we have carbon dioxide, which is acidic. Carbon dioxide is acidic. So we know that since we have carbon dioxide, it's going to be acidic. Since CO2 is acidic. And we can move on to the next. Then we can move on to our next question, our next pre-response question. Right, so our answer here is that it's going to be acidic, pH less than 7. That is it for this question. Stay tuned for next time when we continue looking at more AP Chemistry FRQs. I'll see you then.